All right, so we had covered these two problems, as you can see. I'll give you a few moments to go ahead and get them wrote down. That way you can go over them at your own leisure. And I would highly suggest that you try working on these before we actually give you the answer, or as we go through it. And if we can't read it, it says the following. How much power does a rocket on a track perform if the size is 714 kilograms? To simulate power in the air, it reaches 915 meters per second. It was 1 minute earlier, the rocket was moving at 400 meters per second. Okay? And it also goes on to talk about the track is 356 meters long. So like I said, I'll go ahead and let you write that information in there. As well, and maybe trying to keep the length of this video not necessarily to a minimum, but keeping it a little shorter. One of the aspects that what we could do is just like any other problem, the first thing that we want you to do is write down what we know. Okay. So in this problem, we've got our mass, which equals 714 kilograms. Okay, and then it's talking about these two variables, and since they're measured in meters per second, we know that's not an acceleration, but rather that of velocity. So we'll just go ahead and write them in here for right now. Oops. Meters per second, and then a second velocity. We're not too concerned about which one's which at this time. And then it goes on to talk about a 1 minute time frame. So we've got 60 seconds, or 1 minute. So our time equals 60 seconds. And then any other information that we see is the length of this track was 356 meters. So that's our distance. Okay. Well, what's the question ultimately asking for? Well, it's looking for this, power. And remember, in order to calculate power, you need to find the amount of work done first. And what power is how much work is being done in an allotted time frame, or how efficient that was. So with this given information, we need to find the force first. Once we find the force, we can find the amount of work done. And then ultimately, once we got the work, we can find the power. So what does that mean? First of all, we need to find this. And in order to do that, we also have to have the acceleration. And then we have to find the work. Then finally, the power. Okay? So now we got to continue with these two velocities. And here's our clue. It says it reaches 915 meters per second. And then it says it was 1 minute earlier. So a minute earlier, it was moving at 400 meters per second. So therefore, that makes this an initial velocity, and then that one a final velocity. So in this case then, now we can find our acceleration by doing the following, saying acceleration equals 915 minus 400 divided by 60. Okay? So upon doing so, we take our calculator and say 915 minus 400 equals 515, and then divide that by 60. Oh, excuse me. 8.58 meters per second squared. So since we're kind of constrained with, well, I guess I can erase this now because we have our information that we need. I didn't need to put all this into such a small area. But now we have our acceleration. As we said, 8.58. So once we've got this variable, now we can take this times our mass to give us our force now. Okay? So our force equals 714 times 8.58. Of course, that will give us a variable in newtons. So upon doing that, mathematical operation, 714 times 8.58. It gives us 6126.12 newtons. 0.12, and since it's a force, it's going to be measured in newtons. Okay, so we can cross these two off now. Now we need to find the work. That's fairly simple. Our work equals our force, which we just calculated, 6126.12. And work equals force times distance, which we also have here as well. 356 meters, so that gives us our work now. 6126 times 356. And that will give us a really large number, again in joules because it's measuring work. Okay, 218.0898.72 joules. Okay, so now that we've got our work in joules, to find the power, we want to know how efficiently this work is getting done. So power equals work over time. So we use that 60-minute time frame that we had. Dividing this by 60 will then therefore give us our power in watts. Okay, 36,348.31 watts. Okay, then if we want to take that one step further, sometimes we measure power and also horsepower, and that's a constant. And I want you to think for a moment what you would divide that 36,000 by. Again, giving you a moment to think about that. And yes, we would divide that by 750. Kind of a lengthy problem, as you can see, but with this, if you want to call it a breadcrumb trail, we were able to solve that problem and hopefully get what we consider a valid answer. And one of the aspects that we talked about in class is I would venture to believe that maybe the Air Force or the Army does research like this, because one of the things we talked about in class is when it comes to munitions and explosives, we're always concerned you want the trajectory to be as precise as it can, because munitions that go straight like this just don't quite have the same penetration power as a nice arc like this. So perhaps you'd want that to be at a certain height to break the Earth's gravitational field or gravitational pull in order to do that process of getting that nice trajectory we were just talking about. So 36,348 watts was the answer to number 1 that we just had completed. All right, so the second one, I would venture to believe isn't quite as lengthy, but doesn't make it any more simple though. Sometimes the best way to do these is actually perhaps drawing a diagram of this. And one of the things we talked about in class was maybe sometimes nature's engineers, some of the best ones could be found in the animal kingdom maybe. And in this case, if ants were to build a ramp, What is the efficiency of the inclined plane? Because that's essentially what a ramp is. That is 0.65 meters long while moving a 2.89 kilogram acorn. The height is 0.22 meters, and they place 40 newtons into the acorn. We say they, we're talking about the ants doing or performing that on the acorn. So again, I'll give you a couple moments to write that problem down. And time-wise, what are we looking at? About 10 minutes, so that's not terrible. So one of the things we can do is perhaps draw this maybe while you are writing. If you have to, of course, you can always hit that pause button. And this doesn't necessarily have to be a straight-lined ramp. One of the things we talked about probably in some of these ant hills is probably a spiral ramp, but still a ramp nonetheless. We're just talking about one that is only 0.65 meters long. All right, so the next thing we want to do is write down what we know. We have to know two forces and two distances. Okay? So in this case, we need to know an effort force, an effort distance, a resistance distance, and a resistance force. So let's use some of the terminology in here to help us figure this problem out. And the clue would be looking at what our labels are as far as what these variables can be. And here's one right here. Since it's measured in newtons, we know that that has to be a force. But is that an effort force or a resistance force? Well, we don't know that yet, but it says right here, it says they, in other words, the ants, they're placing 40 newtons of force into that acorn. So that means they're trying to push this acorn up this spiral ramp, for instance. So if they're placing that effort into it, that means this would be an effort force of 40 newtons. Okay? Well, for how long are they placing this 40 newtons into? Well, that would be the length then of the ramp. And in this case, it's saying the length of the inclined plane is 0.65 meters. So that variable is up here. Okay? And the resistance from gravity having an effect on that would be your distance resistance. And in this case, it is not 0.65 meters, but rather 0.22. Okay? And then what's pulling down on that acorn? Just like what we're talking about here, there's a type of unseen, if I want to call it variable that has an effect on this acorn. And of course, that would be gravity, because we've got a mass here. And then with that mass, we can then calculate a force, or that resistance force. They're putting an effort of 40 newtons into the length of the ramp, so that's 0.65 meters. And then the resistance from gravity that's pulling down on this is 0.22 meters. And then notice we don't have anything given to us in meters, but we can find that by taking 2.89, our mass, times an acceleration, and of course that is due to gravity. Then once you get this answer, or excuse me, not this answer, but this terminology set up, then we just want you to do what the formula tells you to do. And it's saying what is the efficiency, so that means you're going to be using this formula. Okay? Not the one where you would say Fe times dE equals dr times Fr. Okay? That's one of those that maybe you're talking about a baseball bat being swung, or maybe you're removing a nail like we talked about in class, where you're moving that crowbar, or maybe you're chopping an axe into a trunk of a log or a tree trunk. But in this case, efficiency, it's a fraction. So what we do is Fr times dr is on top. Okay, so we just do what the formula tells us to do. So 22, or 0.22 times whatever that force is, so which we take 9.8 times 2.89, and that gives us 28.32. Okay, and of course that's all over 40 times 0.66. Again, what the doing what the formula tells us to do. Well, write it in correctly too, I suppose. That would probably help. Okay. So in this case, now we've got 28.32 times 0.22. So that's 6.23. Those two times each other gives us 6.23, and then 40 times 0.65, that gives us 26. So our efficiency is approximately 24%. It gives you a number of 0.24, or actually 0.2396. We take that 9 and round that 3 up to a 4. So that would give you 0.24, but we want it as a percentage, so we take it times 100. And that's how we get 24%. All right, so we were able to keep that under 20 minutes, actually under getting close to 17, but that's what we discussed in class today. Vocab quiz tomorrow, and problem quiz on Friday. All right, catch up to you next time.